degenerate Fermi gas. And we have already seen that n lambda cube by Gs is equal to F3 by 2 Z. Now n lambda cube by Gs, very small, correspond to what is called the non-degenerate Fermi gas, and this occurs when the number density n is small and lambda cube is small. Now lambda cube is small when the temperature is high. So for low number densities and high temperatures, n lambda cube by Gs is small, and this corresponds to the non-degenerate Fermi gas. On the other hand, when n lambda cube by Gs is much larger than 1, we say that the gas is degenerate. Now this can happen when the number density is large or lambda cube is large. Now since lambda cube is proportional to T to the power minus 3 by 2, it becomes large when temperature becomes small. So for small temperatures and high densities, high number densities, n lambda cube by Gs is large. So that means F3 by 2 Z should also be large. Now F nu Z is a function that increases with Z, and therefore when F3 by 2 Z is large, Z should also be large. So for degenerate Fermi gases, the fugacity Z should be much larger than 1. Now as temperature T tends to 0, lambda cube tends to infinity, and this limit is what is called a completely degenerate Fermi gas. And it is easy to do calculations in this case because the Fermi-Dirac distribution function assumes a simple form, and that allows us doing calculations in a much simpler way. So we now consider a complete degenerate Fermi gas, and we already know that the fugacity Z can be written in terms of the chemical potential as Z is equal to exponential beta mu, and in terms of the chemical potential, the Fermi-Dirac distribution function takes the following form: 1 by e to the power epsilon minus mu by kT plus 1. Now as t tend to infinity, this function takes a simple form. For energy values epsilon from 0 to mu, its value becomes 1, and for energy values epsilon greater than mu, it becomes 0. Now the mu 0 that I have written here in this expression is the value of the chemical potential at temperature T equal to 0. So if we look at the way in which the particles are arranged in states, single particle states at T equal to 0, we can see that the occupancy number n is equal to 1 for all states with energy less than mu 0. So that means all those states are filled, and for states with energy greater than mu 0, the occupancy is 0, they are vacant. So if we think of arranging particles in the energy levels that are arranged in the increasing order of energy, we can fill all the states up to a highest value. And this highest value of energy is given a special name, and it is called the Fermi energy of the system. And we denote it by epsilon F. So we can see that n epsilon is equal to 1 up to energy is epsilon F and is 0 beyond. Now we can compute the number of particles by summing over the number of particles in each state, which is given by sum over I ni, where I labels the states. Ni is the number of particles in the state I. Now since the dispersion that we are taking here is given by E equal to P square by 2m, which takes values from a continuous range, in this case from 0 to infinity, as the momentum changes, momentum's magnitude changes from 0 to infinity, we can convert the sum into an integral over energy instead of over states. So that is done in terms of the density of states. So this integral become integral from 0 to infinity, because the lowest value of energy is 0 corresponding to P equal to 0, and the highest value is infinity corresponding to P becoming infinity. So this integral become integral from 0 to infinity d epsilon g epsilon. G epsilon is the density of states, and n epsilon, which is the distribution function, the Fermi Dirac distribution function. Now, the Fermi Dirac distribution function at temperature T equal to 0 is simple. It is equal to 1 up to energy epsilon f, that is from 0 to epsilon f, and is 0 beyond. And therefore, the integrand will be non-zero only up to epsilon f. So we can limit the integral from 0 to epsilon f. Further, in this region, n epsilon is equal to 1. So it becomes simple. So this the total number of particles becomes 0, integral from 0 to epsilon f d epsilon g epsilon. Now g epsilon, as we have already seen, for the dispersion given by epsilon equal to p square by 2m, is given by g epsilon equal to gs, which is a multiplicity factor corresponding to the internal structure of electrons. And in this case, since they have spin half, gs is equal to 2. So gs times 2 pi v by h cube, then times 2m to the power 3 by 2 epsilon to the power half. Now in this integral we can take out all these constant factors outside. So we have all these terms outside. Then integral from 0 to epsilon f d epsilon to the power half. Now the integral is trivial, and it results in this expression for the total number of particles. And the number density is obtained by dividing total number of particles by volume, and we get the final formula for epsilon f. So this can be inverted, and the final formula for epsilon f is given by this, where, as I have told you, this n is equal to n by v, the number density of particles. Now, if you write it in terms of h bar square instead of h square, we have to take care of that 2 pi factors. So then it becomes 6 pi square n by gs to the power 2 by 3 times h bar square by 2m. And the internal energy can be computed in a similar fashion. So internal energy at absolute 0 is sum over I ni epsilon I. Again, the summation is converted to an integral over energy. So this will become integral d epsilon g epsilon n epsilon times epsilon. That's because of this. We can substitute for g epsilon and limit the integral from 0 to epsilon f, because at absolute 0, n epsilon is equal to 1 up to epsilon f, and 0 for energies greater than epsilon f. So this takes a simpler form now. Taking all constant factors outside, this will become these constant factors times integral from 0 to epsilon f d epsilon to the power 3 by 2. In the earlier case, in the integral for n, we only had epsilon to the power half. That's because there was no factor of epsilon here, but while computing energy, we have this additional factor. So epsilon to the power half times epsilon, which is epsilon to the power 3 by 2. The integral can be performed, and we get the final result. So internal energy is proportional to the Fermi energy to the power 5 by 2. So remember, epsilon is given by this expression. Epsilon f is given by this expression, or number of particles is given by this, and internal energy is given by this. So U0 by n, which is internal energy at absolute 0 divided by the number of particles, is this factor divided by this factor. Now all these gs 4 pi b 3h cube 2m to the power 3 by 2 factors are common in both cases, and we have epsilon f to the power 3 by 2 here, whereas we have epsilon f to the power 5 by 2 here. Now instead of 2 pi b by h cube, we have 4 pi, see, instead of this, sorry, 4 pi b by 3 h cube here, we have 4 pi b by 5 h cube here. So there is an additional factor of epsilon f here, and there is a numerical factor of this over here. So u0 by n will result in 3 by 5 epsilon f. Now we use the general formula, general relationship between the pressure, internal energy and volume in these ideal gases, which is PV equal to 2 by 3 internal energy. And using this, since we already know U and V, we can compute the pressure of the gas at absolute zero. So that becomes P is equal to 2 by 3 U by V. Now this can be written in the following way: 2 by 3 U by N into N by V, which is the same as U by N divided by V by N. Now U by N has already been computed, which is 3 by 5 epsilon F. So this is equal to 2 by 3 times 3 by 5 epsilon F, and this quantity V by N is 1 by number density. So V by N is 1 by number density. So it will go upstairs and becomes N. So the result is 2 by 5 epsilon F times N. So that is this result. Now we already know that epsilon F can be written in terms of N as well. So that's given by this equation. Where is it? Yeah. So substituting that over here, we will end up with the final expression for pressure in terms of the number density 6 pi square by gs to the power 2 by 3 h bar square by 5m n to the power 5 by 3. So the Fermi gas has non-zero pressure at absolute, even at absolute zero, and this is arising out of the 0 point motion, and that is mainly because of the Pauli exclusion principle, because all particles cannot go into the lowest energy state, and Pauli exclusion principle forbids more than one particle occupying the same quantum state, and therefore they have to go to higher energy states. Even at absolute zero, they have to obey this principle, and therefore there will be particles in the higher energy states as well. And these fluctuations will lead to, these quantum fluctuations will lead to this pressure. Now we consider degenerate Fermi gas at finite temperatures. So as we have already seen, at T equal to 0, the number density, the Fermi Dirac distribution function is given by this red line. That means it is 1 up to epsilon F, and beyond that it is 0. Now as the temperature changes, there will be variation from this red line, and it will become something like the curve given by the blue line. So that means the occupancy of some levels with energies less than epsilon F is going to be less than 1, and the occupancy of some levels with energy greater than epsilon F is going to be greater than 0 as well. Now the energy width over which this happens is of the order of kT, and similarly over here this is also of the order of kT. So whatever deviation that occurs from the behavior at T equal to 0 is coming from this change in the distribution function, and that happens from energy levels of width of the order of kT above and below the Fermi energy epsilon F. And these energy levels of width of the order of kT about epsilon F are said to be thermally excited. And the fraction of thermally excited particles is of the order of the width of the energy width, which is of the order of kT, and divided by the energy width up to epsilon F, that is epsilon F. So now this can also be written as T by epsilon F by K, and if we define epsilon F by K to be some Tf, then this will become T by Tf. Remember, epsilon F by K has the dimensions of temperature. And this temperature Tf is called the Fermi temperature. Now, noting that the deviation from T equal to 0 behavior is coming from this thermally excited energy levels, and therefore its contribution is going to be dependent on the fraction T by Tf, which correspond to the fraction of thermally excited energy states. We could see that if T is much smaller than Tf, which means the fraction of thermally excited particles is very small, then we will say that the behavior is going to be close to the T equal to 0 behavior. So when T by Tf is much less than 1, or T is much less than the Fermi temperature Tf, the behavior is going to be similar to the T equal to 0, or more or less similar to the T equal to 0 behavior, and we would say that the Fermi gas is strongly degenerate. So T equal to 0 is what is called the strongly degenerate or completely degenerate Fermi gas, and when T is much smaller than the Fermi temperature, we will say that the Fermi gas is strongly degenerate. And on the other hand, when temperature is greater than the Fermi temperature, and so this is when the fraction of the thermally excited states is going to be larger than 1, and in that case the deviation from the T equal to 0 behavior is going to be appreciable, and it is still degenerate, but we will say that it is weakly degenerate Fermi gas. And when T becomes very large, extremely large, then this corresponds to the non-degenerate Fermi gas that we have already considered. So now we limit ourselves to the degenerate Fermi gas, and which correspond to Z is much greater than 1. So when Z is much larger than 1, we have strong Z or large Z expansion of the Fermi Dirac function f nu Z, and this is called the Sommerfeld expansion, and it is given in appendix P.2.3, and the expansion is based on the following result. So if we have a regular function, a differentiable function up to all orders, phi of x, and the integral from 0 to infinity dx phi of x divided by exponential of x minus c plus 1 is given by this series expansion. So the first term is going to be integral from 0 to c dx phi of x plus pi square by 6 d phi by dx evaluated at x equal to c plus 7 pi by 4 by 360 d cube phi by dx cube again evaluated at x equal to c plus the next one the fifth derivative of phi and so on, and this is valid when z is much larger than 1. Now, for large values of z, the Fermi Dirac function f phi by 2 z is given by 1 by gamma phi by 2, an integral from 0 to infinity dx x to the power 3 by 2 e to the power x minus log z plus 1. And this is because we have f nu z is equal to 1 by gamma nu integral 0 to infinity dx x to the power nu minus 1 z inverse e to the power x plus 1. Now z over here is equal to can be written as exponential of minus logarithm of z. So, and substituting this over here, this integral becomes exactly this one. Now we can compare this with this integral, and we see that z can be taken to be log z, and phi of x, so that is this numerator, is equal to be x to the power 3 by 2. And then we can use this expression, the Sommerfeld expansion, for obtaining an approximation for this integral. And remember, we are doing this when z is much larger than 1, and therefore log z is much larger than 1, and therefore we can use this expansion. Now the very first term is given by integral from 0 to z of dx phi of x. So since phi of x is taken to be x to the power 3 by 2, its integral is going to be x to the power 5 by 2 divided by 5 by 2, which is 2 by 5 x to the power 5 by 2 evaluated at x equal to c, but c here is logarithm of z. So this is 2 by 5 logarithm of z to the power 5 by 2. Now this factor 1 by gamma 5 by 2 is 1 by gamma phi by 2 is going to be 3 by 4 square root of pi. So this is going to be 4 by 3 root pi. So the very first term here is going to be 1 by gamma phi by 2, which is 4 by 3 root pi. Then this factor, the first term from this integral, is going to be 2 by 5 logarithm of z to the power 5 by 2. So this is 8 by 15, so 8 by 15 square root of pi logarithm of z to the power 5 by 2. Now we can find the next term is in terms of d phi by dx, which we can easily find because phi is x to the power 3 by 2, and substitute over here, and the term is going to be given by this. Remember, we have already taken 8 by 15 square root of pi logarithm of z to the power 5 by 2 outside. So effectively this is going to be logarithm of, this term is going to be logarithm of z to the power half. Now the first term is logarithm of z to the power 5 by 2, the next one is logarithm of z to the power half, and so on. By taking this outside, we can see that within the brackets the terms are like 1 plus 5 pi square by 8 logarithm of z to the power minus half, and so on. So since z is large, logarithm of z is also large, this term is going to be much smaller than 1. So the next term is going to be of lower order, so that will be going to be, that is going to be smaller than these two terms. So we can sort of neglect the higher order terms in this expansion, and we can stop at this term as a lower order approximation. Now we can do a similar approximation with Sommerfeld expansion for f3 by 2z as well. So in that case, phi of x Now, which was x equal to x to the power 3 by 2 here, now becomes x to the power half, and we can do this integral and take the derivative for the second term, and we will end up with the following expression. So now we have f5 by 2z and f3 by 2z given in terms of a series in logarithm of z. Now the number density can be calculated by n is equal to the total number of particles divided by v, which is gs by lambda cube f3 by 2z. But we have already got an expression for f3 by 2z for large values of z in terms of the Sommerfeld expansion, and is given by this expression, and we can substitute that over here. So we will get this expression. Remember, the first term is, once we have taken out this kt log z 3 by 2 factor. By the way, this kt comes in with log z because we have substituted for lambda cube. Remember, lambda cube is equal to h bar cube h cube by 2 pi m kt to the power 3 by 2. So 1 by lambda cube would be 2 pi m kt to the power 3 by 2 by h cube, and this kt can be absorbed here. So that's what we have done here. So we have kt log z. The reason why we are clubbing them together is we already know that mu equal to kt log z, or in other words, z is equal to exponential beta mu, which is exponential of mu by kt. So logarithm of z becomes mu by kt. Now the terms are within the square brackets, the terms are like 1 plus pi square by 8 log z to the power minus half, exactly the same form we have here. Now kt log z is mu. Okay, so I can call this as mu to the power 3 by 2. Take all these terms to the left hand side and then take to the power 2 by 3. So that will give me mu. So mu, which is kt log z, is equal to, by solving this equation, taking all of them together to the other side, will have h square by 2m to the h square by 2m. Then this goes upstairs, so that will give me 3n by 4 pi gs to the power 2 by 3, because we have to take the power of 2 by 3 to get rid of this factor. Then this goes to the left hand side as 1 by whatever is in this square bracket. So we will get 1 plus pi square by 8. By the way, now I will replace this log z by mu by kt. So mu by kt to the power minus half, then to the power 2 by 3, but it is in the denominator, so the power is minus 2 by 3. Now remember, this factor log z is very, very large. So therefore, mu by kt is much, much large in this case. Or in other words, kt by mu is much, much small, very small. Now, so I have here mu by kt to the power minus 2, which can be written as kt by mu to the kt by mu square. Now kt by mu is a small number, and therefore this quantity is small. Remember, all other terms are going to be smaller than this as well. So this is 1 plus x to the power minus 2 by 3, where x is a small number. And I can use the binomial expansion to expand it into a series. Now, and the series terms would be powers of x. And since x is very small, higher order powers of x can be neglected. And that is exactly what we are going to do now. And along the way, we also recognize that this prefactor that is appearing here in front of the square brackets is exactly the expression for the Fermi energy. So we replace that expression by epsilon f, and then this term is 1 plus pi square by 8 kt by mu square to the power minus 2 by 3. Remember, the terms that is coming after 1 or is getting added to 1 is small, and that is because kt by mu is small. So I can do a binomial expansion and truncate it at first order. Okay, so epsilon f into say 1 plus x to the power n is like 1 plus n into x plus order of x square terms. We will stop at the first order term n into x. So n here is minus 2 by 3. So 1, then minus 2 by 3 into whatever is coming after 1 here, which is this. So that is equal to minus 2 by 3 into this term. There are other terms after this plus as well, but they are all smaller, of higher order in kt by mu. So keeping the lowest order, I just need to consider this term. So this is going to be 1 minus 2 by 3 pi square by 8 kt by mu to the power 2 plus higher order terms. Now simplifying this, we get mu, which is the chemical potential, is epsilon f times 1 minus pi square by 12 kt by epsilon f square, and so on. And the reason why we replace this mu by epsilon f here is the following. Remember, mu is given by this expansion. So what we can do is, we can, instead of mu, we can place this expansion itself. So the first term in that expansion is epsilon f, and the second term is of the order of kt by mu square. So if I replace this mu by say epsilon f plus a term of order of kt by mu square, and then expand it, because this is in the denominator, I can take it to the numerator with the power say minus 1, and if I do that, I will get higher order terms only. So in the spirit of keeping only the first order terms, the contribution, the lowest order contribution there is coming from epsilon f only, so I can neglect all other terms, provided I am restricting myself to the first order term in kt by epsilon f. And that's exactly what we have done here. So instead of mu, I straight away place epsilon f. The remaining terms will be swept into the higher order terms. So mu is now given as a series epsilon f into 1 minus pi square by 12 kt by epsilon f to the power 2 plus other higher order terms. Now from this equation, we see that mu by kt equals Tf by T times 1 minus pi square by 12 T by Tf square plus higher order terms, which will involve higher powers of T by Tf. From this we can immediately see that logarithm of z is going to be much greater than 1, provided T is much less than Tf. So large values of z correspond to temperatures much below Tf, the Fermi temperature. Now this equation 4.28 gives the variation of chemical potential mu with temperature, and that is valid for large values of Z. The internal energy can be calculated using the formula. So U by N is equal to, U is equal to 3 by 2 PV. So U by N is equal to 3 by 2 PV by N. Now this is equal to 3 by 2 times PV by N by V. so P divided by N by V. Now we have the expression for PV and N already obtained here. N by V equal to Gs by lambda cube F3 by 2Z, and P by Kt equal to Gs by lambda cube F5 by 2Z. So therefore PV by Kt equal to Gs by lambda cube times F5 by 2Z, and N is equal to V by lambda cube Gs F3 by 2Z. Sorry, P by Kt equals Gs by lambda cube, then F5 by 2Z. Therefore, U by N becomes P by P divided by 3 by 2 P divided by N by V, which is 3 by 2. Now P is equal to Gs by lambda cube, then this Kt goes to the numerator here, so Kt F5 by 2Z divided by then N by V. N by V is equal to Gs by lambda cube F3 by 2Z. So this and this gets cancelled, and we end up with the relation U by N is equal to 3 by 2 Kt F5 by 2Z by F3 by 2Z. Now we can substitute for the large Z expansion, the Sommerfeld expansions for both these functions F5 by 2 and F3 by 2, because we are now in the degenerate case, and therefore Z is very large. So then this becomes F5 by 2Z is approximated by this expression, and F3 by 2 by this expression. So substituting these two expressions, we will get U by N is equal to 3 by 5 Kt log Z, Kt from this, then a factor of log Z come outside, then this coming from the expression for F5 by 2, and this one which is the denominator here is coming from the expression for F3 by 2. Now since this has the power -1, we can again use the binomial expansion, and this is like 1 plus x to the power -1, and keeping only the first two terms, we will get 1 minus x, but x is given by whatever is remaining after 1, but then the other terms are of higher order in logarithm of z, so we can neglect them. Keeping only the first term, we will have 1, then this is -1, therefore you have a -1 here, then this term pi square by 8 logarithm of z to the power -2 plus higher order terms. So now we can take the product of these two series and keep only the first order terms in logarithm of z to the power -2. Higher order terms can be neglected. So when we do that, I will have the first term coming from this multiplying that, but that is 1. And the second term is coming from, and that is going to be of the order of logarithm of z to the power -2, and that comes from two terms. So multiplying this with this and multiplying this with that. So adding those two, we will get pi square by 2 logarithm of z to the power -2. Now any other term is going to be of higher order in log z to the power -2. So we can sort of neglect them. Now there is one more thing that remains to be done, because logarithm of z has to be replaced by the corresponding expression. Now kT log z is equal to mu, and it has an expression, it has a series expansion, and which is given by this. So kT log z will be replaced by this expression, and we have see this 3 by 5, then kT ln z is epsilon f times 1 minus pi square by 12 kT by epsilon f square plus and so on, and then this term. Okay, so again we have to consider the lower order terms, and there is a now in the second expression, so we have replaced this term, the terms in the square brackets, by this, and that is done in the following way. So I have 1 plus pi square by 2 logarithm of z, but logarithm of z is equal to mu by kT, and mu up to lowest order is approximated by epsilon f. Actually it is epsilon f times 1 minus pi square by 12 kT by epsilon of square and so on, but we need to keep only the lowest order terms, and in that spirit we only write mu as epsilon f and divided by kT. So over here this will be approximated by epsilon f by kT in this expression. Now we have to take this to the power of minus 2, so I will have kT by epsilon f square. So that is where I have made a mistake here, so this should be plus 2. So you have pi square by 12, pi square by 2, kT by epsilon f square, not minus 2. Now I can take the product of these two series and keep the lowest order terms. Again this is obtained as, say you have u here, u by n equal to this, so you multiply with n, so I will get u equal to 3n into this term, so that is 3 by 5 n epsilon f. Now take the product of the terms, 1 and 1 gives 1, then the next term is going to be of the order kT by epsilon f square, and it can come from two terms, so the product of this and that, and the product of this and that. Adding these two contributions, we will get 5 pi square by 12 kT by epsilon f square. So the expression for internal energy is given by u equal to 3 by 5 n epsilon f times 1 plus 5 pi square by 12 kT by epsilon f square. At t equal to 0, obviously this would be 3 by 5 n epsilon f, and so variation from t equal to 0 is the one that is giving rise to this term. Now we can obtain pressure from the formula PV equal to 2 by 3 u, so which immediately gives P is equal to 2 by 3 u by V. So u is given by this, so u by V will give 3 by 5 n epsilon f times this divided by V, but n by V is small n, the number density, so I will get 3 by 5 small n epsilon f and this series. So pressure is 2 by 3 of whatever that is, so that will give 2 by 5 n epsilon f times this series. That's given by this one. Now we can compute the specific heat, and specific heat at constant volume is the derivative of u with respect to temperature at constant volume, and u is given by this, and keeping the volume constant we will have this constant, and the temperature dependence, the lowest order temperature dependence is coming from here, and I take the derivative with respect to temperature, I should obviously get a term of the order of T. So doing that, we will get pi square by 2 n k square T by epsilon F. So for low temperatures, the contribution to the specific heat by specific heat is given by a term which is proportional to T. Now once we got U, we can compute this quantity Helmholtz free energy, and Helmholtz free energy is obtained as in terms of the Gibbs potential as F is equal to G minus PV, but given the chemical potential, G is equal to mu times N. So it's mu N minus PV, but mu is kT log Z. So we have N kT log Z minus PV. Now we have an expression for PV as we have discussed earlier. So P by kT is equal to Gs lambda cube F pi by 2 Z. So PV by PV is equal to V kT Gs by lambda cube F pi by 2, and so that then kT log Z, which is mu is given by this expression, and for P, instead of using this, we have the series expansion given by this one. So P is equal to 2 by 5 n epsilon F times this series. So that can be used. So PV will be equal to this times V. So that will give, say, 2 by 5 n epsilon F into V times this. But V into N is equal to capital N, the total number of particles. So n epsilon F times the series. So over here I can replace PV by this series, which has a prefactor of 2 by 5 capital N epsilon F. So doing that and substituting for kT log Z, which is this series, and rearranging terms, we will get the final result 3 by 5 n epsilon F times 1 minus 5 pi square by 12 kT by epsilon F square plus higher order terms. Now given F, the entropy can be computed since U is equal to since F is equal to U minus Ts, we can compute S as U minus F by T, and I have an expression for U which is given by this one, and we have an expression for F which is given by this, and substitute here, divide by T. The lowest order term is given by pi square by 2 nk square T by epsilon F plus higher order terms in temperature. So obviously as T tends to 0, the whole thing goes to 0, the entropy goes to 0. All other higher order terms will also go to 0 because they are of higher order in temperature. And so this is in accordance with the third law of thermodynamics. The entropy goes to 0 as temperature goes to 0. So in short, for a degenerate Fermi gas, we can use, the fugacity Z is going to be very large, and therefore we can use the Sommerfeld expansion for the Fermi Dirac distribution function, and using which we can compute series expansion for the internal energy, the chemical potential, the pressure, and the entropy. And we can also show that the specific heat at constant volume is going to be proportional to T at for the degenerate case. And this happens when the temperature is much below the Fermi temperature. We now apply this theory to the electron gas in metals. If we consider the electrons, free electrons in metal as a classical ideal gas and do computation, then we will immediately run into some inconsistencies with the experimental result. And for example, if we consider Maxwell-Boltzmann statistics and use the equipartition theorem, which would tell us that the average energy per degree of freedom is going to be half kT, and therefore every electron will have a thermal energy of 3 by 2 kT, and its contribution to the specific heat would be 3 by 2 K, and independent of the temperature. However, experiments does not show this. For metals, it has been observed that the specific heat is actually given by a term that is proportional to temperature T, and another term that is proportional to the cube of the temperature. And to account for this, one has to use the quantum statistics. The electrons could be the free electrons in the metal can be thought of as free. They are not interacting with each other, but they are the levels given by the electronic band in the metal, and therefore they will have an effective mass, and it will not be the same as the mass of free electrons. So we can think of the free electrons in the metal as fermions with some effective mass which we may call m. So which will be different from the mass of the free electrons. Now, Sommerfeld used the Fermi Dirac statistics, because they are fermions, to describe the electrons, and therefore, since they are fermions and we are going to use the Fermi Dirac statistics, we have to find out which regime these electrons in metals belong to. The free electrons in the metal belong to, whether they are degenerate, weakly degenerate, strongly degenerate, or non-degenerate. So this can be found out by finding the Fermi energy or the Fermi temperature of the system. Now, if the temperature at which we are considering the metals, and for us it is the room temperature, so if that temperature is much less than the Fermi temperature of the system, of the metal, then obviously this is going to be a degenerate case. And whereas if the temperature is much below the Fermi temperature, then it belongs to the case of non-degenerate Fermi gas. So the first thing we need to do here is to estimate the Fermi energy and the Fermi temperature. So we note that the electrons have spin s equal to half, and therefore the degeneracy factor Gs is equal to 2s plus 1, which is 2. And then we have the expression for epsilon f. With Gs equal to 2, the expression becomes h square by 2m 3n by 8 pi to the power 2 by 3. Now this m is the effective mass of the free electrons in the band, and not the electron mass, not the mass of the free electron. Now we need to have an estimate of the number density in the metal, number density of free electrons in the metal, and it can be calculated in the following way. If we assume a cubic lattice, and if the size is say A, and if its size is A, then each unit cell will have a volume equal to A cube. And if Ne is the number of electrons per atom, so the number of electrons that is provided by the atom to become free electrons, and if that is represented by Ne, and Na is the number of atoms per unit cell, the average number of atoms per unit cell denoted by Na, then obviously in a volume of A cube, that is within a unit cell, we will have say Na atoms, average number of atoms Na, and every atom provides one electron to become the free electron. So then, every atom provides Ne electrons to become free electrons. So the total number of electrons coming from one unit cell is number of atoms times the number of electrons coming from one atom. So Na times Ne. Now this many electrons will be provided by a volume of A cube. So the number density is estimated by this number divided by the volume. So NaNe by the volume A cube. Now we can consider a typical atom. For example, we consider sodium here, and sodium provides one electron in its outermost shell to become the free electron. So Ne equals 1 for sodium, and Na, which is the average number of atoms per unit cell, and for sodium and for BCC lattice this is equal to 2. Na is equal to 2, and the lattice spacing is given by, lattice size is given by A approximately equal to 4.29 angstroms. Now using the effective mass of electrons as free electrons as 0.98 times Me, which is the mass of the electrons, and we can compute the Fermi energy from this formula, because we have got N and M, and that's all we need. So we will see that the Fermi energy computed is of the order of 5 times 10 to the power minus 19 joules. And dividing it by the Boltzmann constant, we get the Fermi temperature, and we immediately see that this is of the order of 3.7 into 10 to the power 4 Kelvin. So the Fermi temperature is 10 to the power 4 Kelvin. Our ordinary temperatures is something like 300 Kelvin, which is like of the order of 10 to the power 2. So this is almost, the Fermi temperature is almost 100 times larger than the normal temperatures. So we have T less than Tf. So the ordinary temperatures at which we consider the metal is much less than the Fermi temperature of the system, of the metal. So we are in the regime of degenerate Fermi gas, and we can use the theory developed for degenerate Fermi gas here. And there we have already seen that specific heat is proportional to temperature. It's linear in temperature up to lowest order. So for low temperatures, Cv is proportional to T, and the explicit expression is given by this. Cv is equal to this up to lowest order. And this factor is called gamma, the proportionality factor, times T. Now, including the contribution from phonons, that is lattice vibrations, one sees that their contribution for low temperatures is proportional to T cube. So using the proportionality constant delta, we may write the low temperature specific heat of metals as gamma times T plus delta times T cube for small temperatures. So the first one corresponding to the electronic contribution, and this corresponding to the lattice contribution, the phononic contribution. Now if we divide this specific heat by temperature, we see that Cv by T is equal to gamma plus delta T square. Now we can plot a graph of Cv by T and T square here. So if Cv by T is y, and this will become say y, and T square as x, this will become y is equal to gamma plus delta x. So it's with a slope delta and a y-axis intercept at x equal to 0 equal to gamma, which is the proportionality factor corresponding to the electronic contribution to specific heat. So we should get a straight line like this, and the slope given by delta, and this equal to gamma. And this has been verified experimentally.